Make one more video about some of the modules I'm developing in DAQ Factory with the LabJack data acquisition device. This is a temperature recording module or temperature monitoring module. Some of this is technology I'm going to use for the lab I work in for temperature quality control, and some of it will be applied to the backpack dyno for measuring cylinder head temperature and exhaust gas temperature. So what we have going on here, there's the LabJack U6 Pro data acquisition device. I've been experimenting with some various types of temperature sensors. This is one that's sold by LabJack. I can't remember the model number, but it's a voltage outputting silicon temperature sensor. It's actually based on this. This is the LM34CAZ temperature sensor, so that is what I believe is in the end of this thing. It seems to work really well. It's very accurate, has low noise, has good inherent accuracy. You hook it up and you get a pretty good value as far as I could tell, and a fairly fast response rate. It's a little big for some things. What I have here, on the ends of the blue wire lashed together are type T thermocouples. So these, for thermocouples, these don't go very high, only to about 350 degrees Celsius. Most go to about 1,000 or more. But I got these because they have a greater voltage output per degree C. It's still on the order of like 47 microvolts, I think, so it's still small, but it's big for a thermocouple. So these I was hoping to be able to get, with careful calibration, about 0.1 to 0.2 degree Celsius accuracy across about a 5-degree range spanning 37 degrees or body temperature. I have them lashed together so I could see if they kind of perform the same. So this is what I've built in DAQ Factory. You can see the displays on the left. I have each box is a different temperature input. The top one is the silicon temperature sensor, and I'm displaying as a gauge the temperature in degrees Celsius, and then I'm displaying as text the value below it. And then I have buttons here where I could set this minimum and max output down here. So if I press hour, this shows me what the minimum and maximum temperature were over the last hour or day or week. And I set it up to have a little light that turns on by it. Over to the right, I have charts that are scrolling by to show the outputs of the sensors. So let's see, I'll put my finger on the silicon temperature sensor. You can see the gauge on the upper left going up, and you can see the graph scaling up as it increases in temperature. So I just increased the temperature of that about 3 degrees by grabbing it. You can see it has a rather fast response rate. The pink and orange trace are the thermocouples. Now it's a little trickier to measure a thermocouple because the voltage output of a thermocouple is the difference between the sensing tip and the cold junction voltage. So you need to know the cold junction temperature. You need to know the temperature of the ends of these wires where the thermocouples terminate. The whole wire is actually part of the thermocouple circuit, and where it terminates is the cold junction temperature. So right now I'm using the internal temperature sensor built into the LabJack, and that's displayed here as the cold junction temperature. What I'm eventually going to do when I build my real product here, I'm going to use an LM34CAZ that's actually fused to a real cold junction, and I'm going to use that for cold junction calibration. So the graph I have down here is the temperature difference between the two thermocouples. Now these are two identical thermocouples, so I'm trying to see if they respond the same. So let's see. I'm gonna grab them with my finger, try to apply even heat, and you'll see the orange trace going up. The orange trace is actually two traces. It's temp 2 and temp 3. It's actually pink and orange. It's both thermocouples. But you can see these things, their response rate is so even and their output is so even that the trace almost looks superimposed. You can see I'm getting a dip down here in the blue trace. So the dip is the difference between the two. And since there is a little difference in response rate, you get a deviation, a bigger deviation between the two when they're changing. So you can see now that they're cooling back down, and the rate of change is going to start to decrease, and you'll start to see we'll lose this deviation between the two. But at equilibrium, the deviation between the two thermocouples is amazing. It's on the order of 0.02 degrees Celsius, and the response rates are very even. You can see this dip, they only changed by about 0.2, 0.15 degrees, even while rapidly changing. So these thermocouples are amazingly consistent to each other. I'm surprised. And I could read them with fairly low noise. They have about 5 times more noise than the silicon temperature sensor, but that's still on the order of like hundredths of a degree Celsius. So they're very readable directly by the LabJack U6 if you turn the gain up to 1,000. You can see as the thermocouples are cooling back down, the rate of change in temperature is going down, and now the sensors are reading almost more the same. I've played with 2 of the silicon temperature sensors at the same time, and they're very consistent to each other in terms of equilibrium temperature readings, but they do have a kind of different response rate. My guess it's due to how the sensors mounted in the end of the tube. These thermocouples are grounded thermocouples, so the actual thermocouple junction is touching the metal sleeve, so they have really fast response. And I'm actually reading them as single-ended inputs, so you may be able to get better results with differential inputs, but this seems to be working really well. And anyway, that's my temperature monitor.